Hello everyone, this is Dr. Feng Wang from my home, and I hope all of you are healthy and safe at home. Keep on staying at home till you feel absolutely safe outside. We know the whole world is fighting the coronavirus. That's very bad news, but I still have a very good news to share with you today. This is a research result just published by a French team. They found a magic combination to treat coronavirus. In this report, they compared three groups of patients. The control, the black line, the patient did not take any medicine. The, the blue line here, that's the group of a patient who took organic molecules I shared with you called hydroxychloroquine. So it was effective, but not 100%. The real magic combination they figured out was the combination of two organic molecules. The first one is hydroxychloroquine, and the second one called azithromycin. So at day 5, they found it was 100% effective to all patients. That's really a good news we need, and the whole world need at this moment. So I was curious about this molecule is the thromycin molecule, and I did some research. Here is the structure of this organic molecules. It is an antibiotic, and many doctors actually call it a Z-Pak. You probably heard Z-Pak. It's a very common antibiotic molecules. It is a huge molecule. You can see there are many stereogenic centers. I think this is a very good molecules. If you want to practice the skills you learned in identifying the R and S configuration for stereogenic centers. Well, that's the good news. I want to share with you. You see, organic chemistry actually provide you some magic. That's what people really need, particularly at this time. Now let's go back to the fundamentals of organic molecules. Today I want to share with you about amines. We have two types of amines, either aliphatic amine, this is one of the aliphatic amine, or aromatic amine. So in the case of aliphatic amine, basically the first carbon connected to the nitrogen here, this carbon has to be sp3 hybridized carbon. So of course aromatic amines amine the nitrogen atom attached to aromatic ring. This is called aromatic amines or aryl amines. Well, amines in organic chemistry normally serve as a base, either strong or weak bases for organic reactions. So first thing we want to compare the basicity or the strength of the basicity of different amines. Well, base amine or amines, they have a lone pair of electrons. They want to share the lone pair of electrons with others, normally acid. So the more electrons, or the higher electron density in this nitrogen, the stronger the base, again, because they have a stronger desire to share their electrons with the acid. So in the case of aliphatic amine here, the nitrogen has the two electrons, the lone pair of electrons. There is no neighbor that can share this lone pair of electrons with the nitrogen, so it is a base. However, for aromatic amine, this is a very simple aromatic amine. You see, this nitrogen also has two electrons, lone pair of electrons. This nitrogen has I would say, has good neighbors to share this the lone pair of electrons. If we draw the resonance structure, basically we can delocalize, we can shift the 2 electrons from nitrogen to the benzene ring, and we can draw 1, 2, 3, three resonance structures which hold a lone pair of electrons or negative charge. Well, you may see, can we move these 2 electrons, the pi bond here, from aromatic to the amine, to the nitrogen atom here? But unfortunately, we cannot do that because there are 8. If you draw the detailed Lewis structure of this nitrogen, we can figure out there are actually 8 electrons around this nitrogen atom. It's already an octet nitrogen, so this nitrogen cannot take any electron more from the benzene ring. The only way we can move the electron is from the nitrogen lone pair electrons to the benzene ring, which reduces the electron density of this nitrogen. So we can see the basicity of aromatic amines normally weaker than aliphatic amine. So if we expand this resonance structure or resonance concept, we can attach electron withdrawing group here or electron donating group here. Basically, the groups can withdraw electrons this way or donating electrons toward the benzene ring, eventually towards nitrogen, which have different effect. Either increase the basicity of aromatic ring amine or decrease the basicity of aromatic amine. I believe I have many questions in the quiz or in the homework, and I ask you to compare the basicity of aliphatic amine and aromatic amine. And I also ask you to compare the basicity of aromatic amines with all kind of structures. Basically, the fundamental thing, you want to analyze the electron's density around this nitrogen atom. The higher the electron density, the stronger the base. Alright, so in this chapter we are going to discuss only one reaction. Let's make the life easier. So this is the reaction I want to discuss with you. Basically, it's called a diazotization reaction. So it is amine, either aliphatic amine or aromatic amine, react with the sodium nitrate and a strong acid HCl to form diazonium salt. Diazonium either aryl or either alkyl or aryl, aliphatic or aromatic. So we don't have to know the details of this diazonium formation reaction, but we need to remember the reaction condition. Basically, sodium nitrite plus a strong acid HCl to form a diazonium salt. One positive charge and one negative charge in this salt. Why this reaction is important is because this part, the whole part, the azonium salt part, is a very, very good leaving group. And if we have a nucleophile, we can replace this diazonium salt very easily. Here are the reactions we can do from the diazonium salt. If we have a Z normally is a nucleophile, so we can replace the diazonium salt part. Again, this part is a very good leaving group. So whenever this part leaves this aromatic ring, we form the nitrogen gas. Just like water, very good leaving group, plus chloride anion. Chloride is also a very good leaving group. So So we use this diazonium salt to prepare a lot of substituted aromatic molecule like a phenol, basically a benzene plus a hydroxyl group. We just use water. What we know, water is a very weak nucleophile, but because this is a very good leaving group, so the nucleophile water, weak nucleophile water can attack this carbon to form the substituted benzene, which is a phenol. There are more substitution reactions from the diazonium salt, like if we use a copper compound, either copper chloride or copper bromide, we can prepare the aromatic chloride, aromatic bromide. Again, this is diazonium salt part. It's very good leaving group. Whenever we have a good nucleophile, in this case it's chloride, in this case a bromide, we can easily form the substituted aromatic product. And this reaction, actually, I named the reaction is called a Santa-Maer's reaction. So in this reaction, actually, this is a two-step reaction. The first step is the formation of a diazonium salt. The next step is the copper chloride or copper bromide. Either chloride or bromide serves as nucleophile to do the substitution reaction. More reactions, the nitriles, the copper nitriles. The nitriles is also very good nucleophile, can attack this carbon. Again, the driving force is the diazonium salt is a very good leaving group. So one more reaction, if we use hypophosphorus acid to react with the diazonium salt, actually we replace the diazonium salt by a hydrogen atom here to form a benzene ring. Well, why I discuss this chapter, because we just learned the aromatics molecules and the reactions of aromatic molecules. Here is the formation of a diazonium salt is a very good reaction to prepare a lot of substituted benzenes. Basically, I would like to use this like a template, so like a model. So we want to prepare a substituted benzene. This is a very useful way to prepare a substituted benzene. So first we have a benzene ring. We do a nitration reaction to introduce the nitro groups to benzene ring. And we do a reduction reaction to reduce the nitro group into amine group. And next step is the amine group, aromatic amine, react with the sodium nitrite plus the strong acid HCl to prepare the diazonium salt, the very good leaving group diazonium salt. The final step is the nucleophile. This could be a strong nucleophile, could be a weak nucleophile, to replace the diazonium part of this aromatic molecules. And the result is the formation of a substituted benzene. Again, this is one way, and it's a very popular way, a very important way to prepare substituted benzene. We have to know the whole process. It is very long, but each reaction we learn either in chapter 16 or this chapter. Okay, here's another example we can use to prepare a tri-substituted benzene, a tri-bromobenzene here. So if we use the reaction we learned in chapter 16, we can do the bromation of the benzene with either bromine or NBS. So we can introduce one by one. So first, for example, if this is the first one, we will introduce. But it's going to be very hard for us to introduce these two bromines because whenever the first one introduced at this position, this bromine is actually an ortho para director. So if we want to introduce the second bromine, it will be either in the ortho, this is ortho position, this is also position, or para position. It will be hard to introduce the second and the third bromine atom at the meta position. Again, this is the first one. This would be the meta position relative to the first one. This is another meta position relative to this first atom. So again, with the reactions we learned in chapter 16, it will be hard to prepare try 1, 3, 5, 1, 2, 3, 4, 5, 1, 3, 5, tribromobenzene. But with the reactions we learned in this chapter, the formation of a diazonium salt, the very good leaving group, we can prepare different substituted benzenes. Here is the process, how we prepare this 1, 3, 5 meta positions, tribromobenzene. Again, following the procedure we learned in the previous slide, follow this procedure. The first step is to do the nitration reaction of a benzene with the nitric acid plus sulfuric acid to make a nitrobenzene. The second step is the reduction of a nitro group with the hydrogen and using palladium catalyst to reduce the nitro group into amine. This is aromatic amine. Well, the good news for this aromatic amine is we have this amine group here, and the amine is a very strong electron donating group. This is what we learned in chapter 16. And if we do a bromination reaction with the bromine and a catalyst iron bromide, so we can easily form a tri-substituted bromine benzene here. Again, because this amine is a very strong electron donating group, it is a very strong activator in doing the electrophilic substitution reaction. The bromination reaction is a electrophilic substitution reaction, so 3 hydrogens replaced by bromine. And because of this amine is a strong electron donating group, it is also a strong ortho and a para director, which means bromination will be here, and here they are ortho position, and here the third position is para position. That's why we can have this tribromobenzene amine here. So whenever we form this compound, we can do the diazonium salt formation reaction. We react this amine with the sodium nitrite plus HCl to form this diazonium salt. So the next step is how we replace this diazonium salt by a simple hydrogen here. So we use hypophosphorus acid to replace the diazonium salt with a simple hydrogen. So this is the whole process. Again, it looks very long process, but this is a very popular and a very important process in making all kind of substituted benzenes, particularly with some unique structures like this one, 1,3,5 tribromobenzene. Alright, that's a very short, very simple chapter, and means I want to share with you. Let's take a break now.